Yes, we can. Yes, we can.
Okay, great. So, hello everybody, and thanks to the organizers for organizing this nice workshop under these circumstances. I want to contribute to this workshop by talking about how to define entropy out of equilibrium in a microscopic sense for an isolated system, and how to relate it to the second law of thermodynamics. And I think that qualitative picture is quite clear. I tried to sketch it with this quote from a Woody Allen movie down here. But as we already experienced today, I think the quantitative picture is not fully clear. And indeed, I think that the concept I'm advertising today fits nicely into the scope of this workshop, where questions related to finite reservoirs, non-Markovian dynamics, limited information or control about systems was brought up. So let me start with my outline. I will quickly talk about some basics of non-equilibrium thermodynamics before I talk about a candidate for thermodynamic entropy out of equilibrium, and where I also give a couple of mathematical properties, say. And then finally, I will apply it to the question of entropy production in isolated and open systems. So that slide could have been also written by Clausius, I think. So let's consider a system. It's coupled to some heat baths. There might be some work done on the system. And today, I only want to focus on a single heat bath for simplicity. Then the second law, or the concept of introduction, tells you that the thermodynamic entropy of the universe should always increase during any process or stay constant. And then if you basically can distinguish between the system and the bath, you can split up the entropy of the universe into system entropy and into an environmental entropy. And if the bath behaves like an ideal bath, which means that it's basically always well described by an equilibrium state, you can replace this expression by this integral, where Q is the heat flowing into the system, and T, importantly, is in general a time-varying temperature of the bath, okay? And then in the limit where the bath is really, really large and only weakly perturbed, you can basically approximate this T simply by its initial temperature, T0, and then you end up with this form of the second law, which I think is well known from stochastic thermodynamics. And indeed, if you look up the literature, there has been quite a bunch of work already on that, how to derive this in a microscopic way without using rate master equations or something like that. And some of the pioneers of this approach are also sitting in the audience, or they are supposed to sit in the audience. I have no idea, of course. But nevertheless, I would like to criticize these approaches somehow, because if you look at the mathematical derivation of how this is derived microscopically, then you will actually see that none of these three assumptions enters there. So mathematically, they're so general that they're somehow overshooting their physical goal, I would say. And this raises some doubts whether the entropy and heat, which was ad hoc introduced based on this, is really the real entropy and heat, at least for general situations. And for me, I think the problem is due to the fact that in these papers, the authors don't start from a concept for non-equilibrium entropy of the entire universe. And I try to overcome this today and really derive this kind of hierarchy. So the next slide is a little quantum classical dictionary, because I think many people in the audience are more used to classical thermodynamics. But today I will use a quantum notation. I find it more convenient, but actually everything is identical in the classical case and in the quantum case, and equally interesting. So, of course, quantum mechanically, you're in a Hilbert space instead of a phase space, and your state is described by a density matrix, not a phase-space distribution. The notion of Hamiltonian is more or less the same. The evolution equation is either the von Neumann or the Liouville equation. Whenever you see trace operation, you can also think about a simple phase space integral. The von Neumann entropy becomes this kind of continuous Shannon-like entropy. And also importantly today, I will talk about measurements. Quantum mechanically, they're described by projectors with some outcome. And classically, you can imagine that you basically use characteristic functions to partition your phase space into a set of non-overlapping cells. Importantly, these projectors are not necessarily of rank 1, so the rank can be quite large, and this I call the volume of this measurement result, basically, and classically this is simply the phase space volume divided by this normalization constant. And for simplicity, I set today KB equal to 1. Okay, let's come to the second part. I guess everybody has at least 2 candidates for entropy in mind, but they both don't work really well out of equilibrium. Proposal number 1 is the von Neumann entropy simply, but we all know that for an isolated system, the change in von Neumann entropy is always 0. So it doesn't really describe any irreversibility. Proposal number 2 is the Boltzmann entropy, here written maybe in a bit more general form. So I simply assume that you have some macroscopic constraints, which you know, I call them X, and then you count the number of microstates compatible with X, and this is precisely this volume term, dx, then you take the logarithm. What's the problem with that? Well, somehow this entropy is a bit too coarse-grained, so it has really little dynamical information. For instance, if you look at the standard example of a gas which is allowed to expand by taking out a barrier, then even if you would only open the barrier by an epsilon amount, the Boltzmann entropy would instantaneously jump because the available phase space simply doubles. But from a more reasonable entropy, would actually expect that you start with initial value and then you in time you basically approach the maximum value characterized by the Boltzmann entropy. And also it's not fully clear how to apply it to small systems where you can perhaps measure perfectly, then the volume is always equal to 1, so the log of 1 is always 0. So what are you doing if you have a concept which is on the one hand too fine-grained, like the von Neumann entropy, or too coarse-grained, like the Boltzmann entropy? Well, you simply combine these two things, and this is what I call observational entropy, which is formulated with respect to a state rho and an observable x. So x is simply written in this standard spectral decomposition, and px is a probability to get outcome x in the standard quantum Born's rule way, and Vx is this volume, and then you define the observation entropy as a Shannon entropy plus some, you could say, average Boltzmann entropy term. And this definition is clearly not due to me. I think quantum mechanically was first introduced by von Neumann, although actually in a footnote, von Neumann clearly says that he has this definition from Wigner, but to the best of my knowledge, Wigner never really published something about it. And also classically, a closely related notion is coarse-grained entropy, which was actually introduced back by Gibbs already, and which is occasionally used. So although this definition exists in literature, I think there's not too much work on it, especially not in the field of stochastic thermodynamics or quantum thermodynamics. And only rather recently, these three guys revived this notion somehow and really stated, okay, this is a good candidate for non-equilibrium thermodynamic entropy. And they studied the equilibration behavior of isolated quantum systems using this notion of entropy. On the next two slides, I will just give you a couple of mathematical properties of this entropy to make it a bit more appealing, and afterwards we will switch to the physics. So first of all, this entropy is bounded from below by the von Neumann entropy, from above by the log of the dimension of the full Hilbert space. Second, this entropy is extensive in the limit where you expect it to be extensive. So if you measure decorrelated observables on decorrelated subsystems, then the global observational entropy is equal to the sum of the marginal ones. And there's a certain equivalence relation which tells you that the observational entropy of some state equals the phenomenon entropy of the state if and only if you can write the state as a convex combination with arbitrary probabilities px of these omega x, which I call generalized microcanonical ensembles. So what is omega x? Microscopically, it's simply a distribution which is equally distributed over all microstates within a given window, within a given measurement window x, but x does not need to be the energy. In that sense, I prefer to call it generalized microcanonical ensemble, but the idea is the same. So please remember in particular this third equation, because now we will switch to a dynamical picture. So now I'm interested in how does observational entropy actually change due to the evolution, and there are actually two contributions. So observational entropy can change due to the fact that the state is evolving, or in principle you can even consider different observables at different times. So you can switch those as you like, and I will always set the initial time to be 0 in the following. And then there are two results which are already somewhat precursors of thermodynamics. So there's some kind of second law telling you that if the initial observational entropy coincides with the phenomenon entropy of the initial state, and remember just the previous point I mentioned about this equivalence, then the change in observational entropy is always positive. And this kind of theorem or result, I think, was perhaps not in this general form, but more or less in that form already noted also by other people. And then there's also the fluctuation theorem, which you can actually prove under the same condition as the second law. You can show that the exponential of minus the fluctuations in the observational entropy, this is always equal to 1 as average. And if you want to know more technical details, you can look them here up in the slides later on. Let me just mention this theorem was also very recently actually noted in another work as well. Actually, these two guys that you write an even larger class of fluctuation theorems, where this is just one kind of application, one could say. So far this was all mathematics only, and importantly, I'm not claiming that for any choice of observable x, the observational entropy is a good candidate for thermodynamic entropy, but one has to choose the observables appropriately. So let's come to entropy reduction. And of course, a good choice, you might already guess it, are energy measurements. Let me introduce some notation. The spectral decomposition of the stationary Schrödinger equation is simply write it like this, with eigenvalues and eigenstates of the energy. And I define coarse-grained projectors, which sum over these projectors for all energies within a given window of width delta. So the measured observable is somewhat like a coarse-grained energy measurement, which in the limit for delta going to 0 becomes the Hamiltonian. And this is just a repetition. That's how the observational entropy looks with respect to this measurement. And what I will also define is the set of equilibrium states, capital omega, which is somewhat larger than the standard class of equilibrium states, because I allow simply all combinations, probabilistic combinations of these microcanonical states. As a side remark, so delta, in principle, in theory, it's a free parameter, which experimentally, of course, it's a bit more subtle. You have to choose it somehow small enough. But today I want to put away like experimental subtleties and simply use it as a theoretical tool to study entropy reduction in quantum systems and classical systems. So that's why I will leave the dependence on delta implicit in the notation. Okay, then let's consider heat and work in isolated systems first. So an isolated system evolves according to the standard von Neumann equation, and I assume its initial state is a member of this class of equilibrium states. And then the standard definition of work is the following. We simply look at the change in internal energy of the entire universe, which is given by this expression. And we define this to be the work done on the system. And on this slide, let me simply assume that this is always positive, okay? And I do not want to question this definition per se. I think it has its justification. But somehow I think what one would more like to know is actually how much of this work, which I've defined here, is actually really recoverable work. So how much of this work can I basically recover in some sense if I use only macroscopic operations? So clearly, we all know that when I have perfect control about every system of my universe, I can recover all of the work by basically applying time reversal, symmetry operations, and all of that. But we all also know that this is not really possible in our world, and that's the reason why actually work gets degraded into heat. And a good candidate to define recoverable work in these isolated systems turns out to be that. So it's a change in internal energy, simply this expression. And then I subtract an integral over the observational entropy with respect to a fictitious Gibbs ensemble. And this Gibbs ensemble is basically evaluated with respect to some effective non-equilibrium temperature Ts star. Okay. So what is this temperature? Well, I mean, consider at each time you have a fixed internal energy of your system. And now imagine that you can basically bring in a super bath, which is really ideal and which you can couple very weakly to your big system. And you wonder, what is the temperature of the super bath, which when coupled to the system would basically cause no change in internal energy. And this temperature you define to be this Ts star. So it's the temperature of a super bath which causes vanishing heat exchange. And why is this definition good? Well, at least I have the following result, which somehow defines reversible processes. It says that the recoverable work is identical to the total work if and only if the process is reversible, so there's no change in observational entropy, if and only if the state remains in the somewhat larger class of equilibrium states. And if any of these things is not fulfilled, you could actually introduce a concept called the remaining heat, which is simply the change in energy minus the recoverable work. And this would be then always positive. Okay, now on my final slide, let me switch to open systems. So now we consider that you have a standard system Bar's Hamiltonian, and I consider only the system to be driven, and I assume that the system Bar's state initially is a product state, the system is an arbitrary state, and the Bar's is in this equilibrium class. And as my relevant observable, I choose a coarse-grained measurement of the Bar's energies. And actually for the system, I can choose whatever I like. And this I do in view of the typical situation that your open system is really, really small and you really have precise control over it in a lab. Of course, this doesn't have to be the case. So this could be also a coarse-grained observable or whatsoever. However, under these conditions, already from what I showed you in the mathematical part, we know there's a fluctuation theorem and of course a second law telling you that the change in observational entropy is always positive. Now let's come more to the standard Clausius inequality. And actually what I can show, I'm not doing it here, but I can apply this notion of remaining heat for the bars, and I can show that this integrated is nothing else than the change in Bar's energy. And I can actually show that the change in observational entropy of the system plus this integral over the remaining heat divided by this effective temperature is always positive. And it equals the change in global observational entropy exactly in the limit where my Bar's is well described by an equilibrium state with a time-varying temperature. And finally, if I go to the weakly perturbed Bar's limit, by which I mean that the coarse-grained probabilities at time t for the Bar's energies can be expressed in some sense as an epsilon correction to the initial energies, then I get within first order of epsilon, I get this change in observational entropy is simply the change in Bar's energy over T0, which you then identify as heat, and then you get the standard second law. And what I really want to emphasize is really you have this kind of hierarchy. You start from this general thing, then you do a bit more of assumptions, and you really go down here to the, let's say, standard case in stochastic thermodynamics. Just to mention, you can also look at the remaining heat in the total system Bars complex. And then somehow, you know, the value of that will depend on how much control you assume over the system Hamiltonian. If you have only very limited control, you can actually show that this remaining heat is the total work minus the change in equilibrium free energy, which is known as the dissipated work. Or if you have really full control over the system, then this becomes the total work minus the change in non-equilibrium free energy. In both cases, it's always positive, and these inequalities are, of course, also well known in the literature. Okay, that was all. Now I come to my conclusions. So all the details are here in this preprint. Actually, some of the basic ideas go back to an earlier preprint of me. And my main messages are three messages. So first of all, I think observational entropy is a good candidate for thermodynamic entropy out of equilibrium. And here I want to explicitly acknowledge once more the nice work of Dominik Safranek, Josh Deutsch, and Anthony Aguirre, which motivated me actually to consider all that. And I think Dominik is also in the audience. So in case we have a discussion later on about these topics, perhaps we can include him also more because he's definitely the expert here. My second point is that given that you believe the first point, then I've really shown you what I would call a consistent derivation of the second law, because I really showed microscopically that it's a thermodynamic entropy of the universe, which is not decreasing, whereas previous works did not contain this statement, at least not in general. Then the last point is that I want to emphasize this is really an extremely flexible tool. I haven't talked about all its applications, but you can use it for one or multiple bars. I showed you already that it goes beyond Gibbs states in the bars. I would even claim you can apply it to pure states in the bars if you like. And it also includes a large class of correlated states. In case of one or multiple bars, it doesn't matter. So it's really a unifying perspective on all kinds of possible second laws which you can have. Last but not least, let me shortly acknowledge a couple of people here. You can read the names on your own. Those haven't contributed technically, I would say, to that project, but definitely they've influenced me a lot about the way I think about these kind of issues. And of course, let me also acknowledge Andreas Winter, who really contributed as one of the co-authors. So thanks a lot, and then I would be looking forward for questions.